everyone. In the last 5 videos, we covered the following topics: Laplace transform, property of the Laplace transform, solution of differential equation, and the frequency response of a system. In the next and last 2 videos, we will be talking about the block diagrams and system realization and filter design by poles and zeros placement. So this video we will cover this topic: block diagram and system realization. And the topic here is, if an engineer designed a system and gave you the transfer function h of s and ask you to build this system in the lab using amplifier, resistor, capacitor, or what components in the lab, how will you build this system, an actual system? And this is the topic of today's lecture. So let's review common systems and their transfer function. The first one is the time delay. So a time delay system, this is the equation that describes the system. You have an output, it will be the same as the input delayed by tau. If I want to find the transfer function, then I will do the Laplace transform, use shifting property, and that will be y of s equal x of s e minus tau s. If I divide both sides by x of s, I will get h of s. And this is the transfer function for a time delay system, and the delay is tau. The next one is a differentiator, and a differentiator is the output y of t equal the derivative of the input signal. Again, I find the Laplace transform of this equation, and using the differentiation property, y of s will be sx of s. If I want to find what h of s, divide both sides by x of s, so then h of s will be just s, which is y of s over x of s. And an integrator, the output will be the integral of the input. To find the transfer function h of s, I just do the Laplace transform, and the output will be just the input divided by s in the Laplace domain, so the transfer function is 1 over s. If I want to find the frequency response, h of omega, for a derivative, it looks like this. So as the frequency increase, the output increase. So a signal with noise will give you a huge output because the signal will be amplified by its frequency. That's the amplification. So we're going to avoid using a differentiator in building a system, and we will be using an integrator, because the integrator, if I plot this, looks like this. H of omega, the magnitude for an integrator looks like this. If you replace s by j omega, and the magnitude, you take the j out. So it will be 1 over omega. Here it will be omega. So in this, we're going to be using the integrator in system realization. Let's do another review before we start, which is the block diagram. This is a block diagram of a system. This is the input, this is the output. Now, sometimes when you have a big system, it's better to break it to 2 small systems, and you can put them in cascade or in parallel. In this case, if you break the system to 2 subsystems, h1 of s and h2 of s, and you connect them in cascade, then what is the transfer function of the whole system here, which is this one? It will be h1 of s times h2 of s. And it's easy to derive these. The output w of s of this subsystem is just the input x of s times the transfer function h1 of s. Now for the subsystem h2 of s, the input is w of s and the output is y of s. So the output y of s will be w of s times the transfer function h2 of s. If I substitute the value of w of s using this equation, then it will be x of s, h1 of s, h2 of s. So if I represent these cascade systems as one system here. The input is x of s and the output y of s. This is the equation. That's the output. This is the input, and this is h of s. So two cascade system, the total transfer function is just a multiplication h1 of s and h2 of s. Same thing if I connect them in parallel. So if I want to find what is the total system here, two subsystems connected in parallel, then again the equation will be, let's call this here w1 of s, and let's call here w2 of s, this branch. So in this case, w1 of s will be the input x of s times the transfer function h1 of s. Now this output w2 of s will be the input x of s times this transfer function h2 of s. Now if I want to find the final output y of s, it is just this signal plus this signal. This is a summing amplifier. So that will be this one plus this one. Now if I take x of s as a common factor, then it will be, and this is the total system for two subsystems connected in parallel. Just h1 of s plus h2 of s. Okay, the last one is feedback interconnection, and that's very important. If I want to describe this whole system as one block here, then what's the transfer function? So let's derive it. Well, first I'll describe the equation for this subsystem. The input is E of s, the output is y of s. So y of s equal the input times the transfer function of the subsystem g of s. Now let's describe this signal E of s. What does it equal? Well, it's equal x of s, this signal, and the signal in this branch. And the signal in this branch, let's call it w2 of s, and let's find first w2 of s. So w2 of s is the output of this subsystem, and the input is y of s. So then I can say w2 of s equal the input, which is y of s, times h of s. Now let's describe E of s here. E of s is this signal x of s, and you add to it, look here, this is negative feedback, negative times w2 of s. Now let's substitute the value of w2 of s using this equation. So then E of s will be x of s minus this quantity. And again, I will remove this quantity using this equation. So then this equation will become, because at the end I want to find one equation that has only the input x of s and y of s. So this equation will be y of s equal E of s here, I'll substitute this value, multiplied by g of s, and this equal, okay, now I will put all y of s on one side and everything x of s in one side. So I'm going to bring this to the front of the equal sign. So this will be y of s plus y of s equal, only this left after the equal sign. And I can take y of s as a common factor here. So then I will have 1 plus h of s, g of s equal, let me just put this as g of s, x of s. And finally y of s equal, divide everything, both sides, by this quantity. I will get g of s divided by 1 plus h of s, g of s times x of s. So this is the transfer function of the whole thing here. And that's the same as here. G of s here is the forward subsystem. H of s here is the negative feedback because of this negative sign. And we're going to use this equation a lot, so keep this in your mind. How this equation represent these feedback subsystems. Okay, with this feedback, now let's move on to system realization. So you may have a transfer function that describes system of n order. And usually for a stable system, n will always be equal or larger than m, which is here. Always this is going to be the case. And we want to use integrator, amplifier, summing, or adders. So the first step always, if you are given h of s, you want s to the highest power to have a coefficient 1. So if a problem was 3, divide everything by 3. So the coefficient here always 1. The next step is I need an integrator. So I will divide every component in the numerator and in the denominator by s to the power of n. N here could be 3 or 4 or 5. So I end up with all integrator. And then I use canonical form 1 realization or canonical form 2 realization and the transpose realization. So let's move on with an example and see the steps. So assume you have this third order system, h of s. Then the first step is, yes, this is 1, good, so I don't have to do anything. The next step is divide every numerator element and every denominator by s cube. When you divide this by s cube, you get b0. You divide this by s cube, you get b1 over s. You divide this by s cube, you get b2 over s squared. This one, you get b3 over s cube. Same thing, you divide this by s cube, you get 1. Here, you will get a1 over s. Here, you will get a2 over s squared, a3 over s cube. So that's what we did. We divide every element in the numerator and the denominator by s cube. Now the next step is, how do I break this system so it will be two subsystems connected in cascade? If I use the canonical form 1 realization, then the numerator will be my first subsystem here, and I will call it h1 of s. And 1 over the denominator will be my second subsystem, and I will call it h2 of s. So now this system here, I described it as a 2 cascade subsystem. h1 of s is the numerator, h2 of s is 1 divided by the denominator. And the input is x of s, and the output here y of s, and they call this w of s. Now how do we build this system? If I use the canonical form 1 realization, so let's see how we're going to build this. I'm just rewriting this equation. It's the same here. So I can say, instead of rewriting it this way, h of s this way, I will rewrite it this way in terms of input and output. So I will say h of s equal y of s over x of s. Then I will multiply both sides by x of s. So then this will be y of s equal x of s times this times this. Now this input will be going to the subsystem first and give you w of s. Then w of s will go to this subsystem as an input, and you will get y of s. So let's draw the node for x of s. So that is x of s here. That's the input. You connect the input. That input could be coming from a sensor, temperature sensor, microphone, and it's going to this subsystem. Now what is this subsystem? Well, B0 is just an amplifier, so it will go to an amplifier of gain B0, whatever, it could be 3, 5, 6. Then x of s also will go to this 1 over s integrator. So then x of s also go to an integrator and then amplified by B1. Also x of s will go to a second integrator, 1 over s squared. So then it will go here, one integrator and second integrator, and amplified by B2. And again, x of s will go to a third integrator, 1 over s cube. So that's a third integrator, and amplified by B3. Now I have to add all these components, plus, plus, plus. That means I have to add this node, this node, this node. So I'm gonna have here a summing amplifier and add these to it, and I have here a summing amplifier and add it here, and I have here a summing amplifier and I add it here. And everything here, the output of this subsystem, I call it W of S, which is here. Now W of S will be going to this subsystem. Now if you look at this subsystem here, it really a negative feedback. G of S is 1 and this will be H of S. So you can think of it as G of S divided by 1 plus G of S, H of S. And that is what we learned is the negative feedback here. That's G of S. So in this case, G of S is just 1, so that is just 1. So that will be this 1 here. The negative feedback here, H of S, is all this quantity. And that GS is 1. So this time 1 is just this. And what is this 1? This is an integrator amplified by A1. And look here, this is negative. Since I'm using positive summation, I will then put the amplification negative. And then I have a second integrator amplified by A2. Again, because when we derive this equation, we have this negative, then I'll just make it minus A2. And a third integrator and multiplied by A3, so that's minus A3. And I have here plus, 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 so I add all these terminals. And the output will give me all these, will give me Y of S, which is here. When you build your system this way, that's the direct form realization. Is this the ideal way to build your system? No. There are too many integrators, too many summing amplifier, and canonical form 2 realization will make it easier to build it. And all you have to do is just make this subsystem first, and this is second. That means make this H2 of S to come first, then H1 of S second. So your system will be then H2 of S first, which is the feedback, this one, H1 of S, which is this one, second. In equation, it means just change the order of this term with this term. So X of S will see this first. Then W of S will go to this second. And that will be form 2 realization. Graphically, it means I move these to be here and I move this one to be here and connect them. And if I do this one, let's see it here. See, I just changed the order in terms of equations. This is canonical form 1 realization. The feedback is the second subsystem. So now if I cut it here and move these to be first, that will be this. And then this subsystem here to be second, that will be this. So that's form 1 realization. Now this will be form 2 realization. All you did, you changed the order of H1 and H2. Now I can simplify this even more and see the advantage of form 2 realization. See, this node here and this node are the same. They are just connected by piece of wire. So the signal here and the signal here exactly the same. So this signal is going to an integrator, this signal is going to integrator, and they are the same. Why having 2 integrators? So I would just combine these to here, to one integrator. And the output of this signal here is the same as the output here. And this will go to minus A1, so this will go to minus A1, and this will go to B1, and this will go to B1 here. Same thing, I combine these, I get this, and I combine this, I get this one. And this is form 2 realization. Now the advantage of form 2 realization in comparison to form 1 realization, look here. If you have n order, let's say n is 10, the order of the system, then you're going to have 10 integrator here, 10 integrator, 20. Here you're going to have only 10. So you cut your integrator by half. And the less component in the system, the less error. And the system will be faster. So definitely Form 2 realization is our choice. And we will see how can we get Form 2 realization without going through Form 1 realization first, then switch them here, then combine them here to get the final. I can build Form 2 realization from this equation directly. And let's see how to do that. So again, let me write this in terms of y of s and x of s. This is y of s over x of s. I can bring x of s here. So y of s will be so if I want to draw this system, first let's draw the node for x of s. So that is the input. The input will go first to this feedback subsystem. So g of s is 1. So that's g of s. And the feedback is all these. H of s, the feedback is all these. So what is it? It is an integrator 1 over s amplified by a1. And again, because this is negative feedback, I'll just make this negative, so the summation will be positive. Then go to a second integrator amplified by a2, so that's minus a2, negative feedback, and a third integrator negative a3, and then I sum them up. And the output of these here, I call it W of S. So that's W of S. Now W of S will be the input to this one. So W of S will be amplified by B0. So that's B0. Also, W of S will go to this integrator 1 over S, then amplified by B1. So W of S will go to an integrator and amplified by B1. W of S will go to a second integrator, that's 1, second 2, and amplified by B2. Finally, W of S will go to a third integrator, so that's 1 here, 2, third, and come out amplified by B3. And then I sum them up here, sum, sum, sum. So that will be, and this is my output here. I build it directly from this equation without doing canonical form 1 and then switch the subsystem. You can look at this equation, start building this negative feedback, then you look at this subsystem and start building this second subsystem. And that is canonical form 2 realization. The next one is, and the final one, is the transposed realization. In transposed realization, this is another way of building a system by transposing an existing system. For example, let's say we have this form 2 realization. If I want to find the transposed realization of this system, then I follow the following step. Reverse all the arrow direction without changing the scalar multiplier's values. That means this direction here, reverse it so it will be this way instead of this way. Same thing here. Instead of this way, now it will be this way. And all of these. And this one, instead of going this way, it will go this way. And I don't change the scalar value. This is still minus a1, this is still minus a1, this is still bn minus 1, and this is bn minus 1. The second step, replace branch nodes by adders and vice versa. See, this is a branch node. A current or input go in and then branch out. So I will replace this by an adder. So that will be this one here. Same thing, this is a branch node, a current or input coming this way, and then it goes this way and this and branch out. So I'm going to replace it by this summing amplifier. a summing amplifier will be replaced by a node. So that summing amplifier will be replaced by this node. And it makes sense that now this will be branched because you don't need a summing amplifier here. There is an input going this way, then it's branched out here and here. So all these summing amplifier will be branches. All these branches here will be summing amplifier. The third step, replace the input x of s with the output y of s. So this x of s will be y of s, and this y of s will be now x of s. And this is the transpose. And to make the flow of the inputs, instead of going from right to left, make it the traditional way, go from left to right, then I have to rotate these 180 degree. So then rotate it around this axis 180 degree, and that will be this one. And this is the transpose. Now x of s will be here, y of s will be here, and these branches here, b1, bn minus 1 will be this one, and those one here will be this one. And this is the transpose of form 2 realization. Now, if I want to find the transpose of form 2 realization, do I need to find first the form 2 realization from this equation, then do the transpose to get to here? No, actually I can go directly from this equation to here without finding form 2 realization and then the transpose. If I write these equations as y of s times h of s times x of s, then it will be something like this. So remember, the feedback will be the second subsystem. So first I draw the node of x of the input, and x of s going to this amplifier, so that will be b0. Then x of s going to an integrator and amplifier by b1. So then I need another amplifier b1, and it goes to an integrator. And I sum it with this. X of s times b0, x of s integrated times b1. Then x of s go to a second integrator and amplified by b2. So then x of s here go to a second, first amplified by 2, then it go to a second integrator. So that would be 1. You take it with this summing and then goes to the second integrator and back here and sum it up with this summing amplifier. Then x of s go to b3, so x of s again now go to b3, and it's integrated 3 times. So that would be 1 integral, and then that will be the second and then the third. So I need a summing amplifier because this will also be integrated and this will be integrated. And the output of here will be this x of s going to this subsystem, and I will get w of s. So let's call this w of s. So now w of s is going to this feedback system. So g of s is 1, so that is the 1 here. And then it's going to this feedback, which is an integrator amplified by a1, and it's negative feedback. So then it going a1 negative, and integrator 1 over s will be here. 1 over s and goes here and back here. Then it go to a second integrator and amplified by a2. So this negative feedback, that's minus a2. So then the flow will go this way, then the first integrator, then the second. And third integrator will be this way. And it goes 1 over s cubed. It will flow this way. Then this first integrator here, then flow second integrator, then flow third integrator, then back. And that will be y of s. So I can go to the transpose without finding form 2 realization, then do the transpose. Now, which option do you want to use? Form 2 realization or the transpose? Which one will use less component, less subsystem? They are almost the same, but it depends on the circuit. Sometimes it's better to use the transpose. Sometimes it's better to use the Form 2 realization. In general, the transpose will have less summing amplifier. For example, here you have 1, 2, 3. Here you have summing amplifier 1, 2, 3, 4, 5, 6. Let's take an example to demonstrate how to build Form 2 realization and the transpose. So let's find the canonical Form 2 realization. I have this transfer function, h of s, and I want to realize this system. Let's write h of s here. So the first step is divide numerator and denominator by s to the highest power in the denominator. So that will be just s. So this will be 5 over s divided by 1 plus 7 over s. If I want to do Form 2 realization, then the negative feedback will be the first subsystem. So that will be 1 over the denominator times the numerator. So I can express these in terms of y of s and x of s as. So the node for the input x of s will be here. It will go to the subsystem, which is a negative feedback. So g of s here is just 1. Then it go to an integrator. Then amplification of -7. And the whole thing here is w of s will go to this subsystem, which is an integrator 1 over s. So this w of s will go to an integrator, then amplified by 5. And that's y of s, this one. And later on, we will see how do we build this integrator, how do we build this amplifier. Okay, let's do the second one here. Again, I can express this h of s. I will divide numerator and denominator by s. So this will be 1. S divided by s is 1. And this will be 1 plus 7 over s. I can express this y of s equal x of s. Now this is just a negative feedback subsystem. So it's just one subsystem. I don't have anything here, just one. So to build it, this is the node of the input x of s. It's going to g of s, which is just 1. And then this is the feedback subsystem h of s, which is an integrator amplified by -7. And then summed up here. And then it goes to 1. And this is the output, which is this. Let's do this one, see. So h of s is s plus 5 over s plus 7. So I divide by s. This will be 1 plus 5 over s, 1 plus 7 over s. Let's do the last one here. This one will be, I can write it as h of s. In the denominator, s is to the power of 2. So I will divide numerator by s squared and denominator by s squared. And this will be 4 over s plus 28 over s squared divided by 1 plus 6 over s plus 5 over s squared. And 1 over the denominator will be my first subsystem. And the numerator will be my second subsystem. And this h of s, I can express it as y of s times x of s. To draw this block diagram, this is my node, the input. First, it goes to this subsystem, which is the feedback, negative feedback. So this is g of s is 1. And this is the negative h of s, the subsystem. So it's an integrator amplified by -6, then a second integrator amplified by -5, and then I sum them up. Now the whole thing here will give me w of s, goes to this subsystem. So that's W of S. Go to this subsystem, which is an integrator amplified by 4. So that's the integrator and amplified by 4. Then W of S go to a second integrator, which is this one, and amplified by 28. And I add these and I add these. So I add this node with this node. And the output will be Y of S. Now, if I want to draw the transpose of this one directly from this equation, well, this I can rewrite it such that this will be first and this will be second. So it will be Y of S equal, and then the node X of S will be here. It will be amplified by 4, then go to an integrator. Then X of S will go to amplification of 28 and a second integrator. So that will be the first integrator, and that's the second integrator, and it comes here. And the whole thing here is W of S. So that is here, W of S. Will be going to this feedback system. So G of S is 1, so that would be the 1, and that's H of S, the feedback. It's an integrator with amplification -6, and that would be the first integral here, here, and come back. Then a second integrator with amplification -5, and it go to this integrator, then here, then a second integrator and back, and that will be the output Y of S. So this is form 2 realization, and this is the transpose realization of form 2. Here I have 1 summation, here I have 1, 2, 3 summation. Okay, the next topic is building the subsystem in cascade or parallel realization. So you have big system and you want to break it to smaller systems, subsystems, and then you can either cascade them or connect them in parallel. What are the differences between connect them in cascade or in parallel? We will see later parallel is much faster and can tolerate noise more than the cascade. So if it's possible to do it parallel, then go ahead with parallel realization, and we will see why. Let's clean these. So if I have this system and if I want to build it as 2 subsystems connected in cascade, the first thing is to factor out the denominator. So that will be 4s plus 28 over s plus 1 times s plus 5. Then I can express these multiplied by 1 divided by this. And now I have 2 subsystems. One is this one, H1 of S, and this is the second one, H2 of S, connected in cascade. And all these is just this H of S. Now I can realize these, and I can realize these, and connect them in cascade. So let's realize H1 first. So if I realize H1 first, which is this one, I divide numerator and denominator by S, so I will have 4 plus 28 over S, 1 plus 1 over S. My second subsystem is this one. I divide numerator and denominator by S, so that will be 1 over S, 1 plus 5 over S. This is H1, this is H2. To realize this system, I will use form 2 realization. So this I can express it as, first the feedback, 1 over 1 plus 1 over S, time the numerator, 4 plus 28 over S. And let me build this system first, which is H1. It will be X of S here, G of S is 1, the feedback 1 over S, H of S, which is this integrator, amplified by 1, which is -1 negative feedback, and the summation. Then the output here go to this subsystem, which is amplification by 4, and then go to the integral, go to this integral, and then amplified by 28. And then I sum them up by this plus. And this is the out. So all I did right now is I built these. If I call this is x of s and this is w of s, that's what I have here. So all I did is this subsystem. Now let's build this. So again, this one will be first the feedback 1 over 1 plus 5 over s times the numerator 1 over s. The input to this is w of s. So that's this one. So let's build this one. So this is g of s is 1, so that is 1. And it's going to a feedback s then amplified by 5. This integrator minus 5. And the output of this system will go to here. So this is the output of this system here. Will go to 1 over s integrator, so it will go here and then it come out here. So this one is h1 of s, that's here, and this one h2 of s, which is here. And they connected in cascade. They're connected by this section. Now let's build the same system using parallel realization. So to do this, we need to do partial fraction expansion. That means I express this one as h of s equal a over s plus 1 plus b over s plus 5. Then find a, find b, like the way we did it when we do the inverse Laplace transform, and you will find it to be 6, a and b will be minus 2. So let's build this system then. Let's first build this one, this system. So this 6 over s plus 1, I divide numerator and denominator by s, so that will be 6 over s, 1 plus 1 over s. And if I build this system, let's make the input node x of s here, and I can express these first as the feedback, then going to the subsystem, which is the numerator. So these, the input g of s is here, 1, and the feedback h of s is just an integrator with amplification 1, which is negative 1. Then this one will go to an integrator, so here is w of s, go again to an integrator, then amplification by 6. So I built this system. The input is x of s, the output I can call it just w1 of s. Now let's build this system. 2 over s plus 5. I can express it, divide numerator and denominator by s, so that will be 2 over s, 1 plus 5 over s. And I can express these as the feedback 1 over 1 plus 5 over s times the numerator, the second subsystem, 2 over s. Now if I build this system, see here, if I express these as y of s over x of s, and then I multiply x of s time here, and x of s will be also multiplied by here. So x of s is an input to this, and you get w1 of s, which is this. X of s also go to this system, and you get another output. So let's draw the block diagram for this subsystem here, which is this one. So x of s is here. Again, it go to this feedback, g of s is 1. Then h of s is an integrator with amplification 5, negative feedback minus 5, and to this summation. Then this is w of s is going to this subsystem, so that's w of s here. It go to an integrator again, so that's the integrator, then amplification by 2. And this is, let's call it w2 of s. So we build this, and we got w of s here. So when the input go to this subsystem, you get w of s. Then when the inputs go to this subsystem, you get w2 of s. So it will be this one minus the output of this one. So you take w of s to a summing amplifier, and this minus, you can express it as here -1, and this is +1. That's one way. Or you can just make this -2 and just make this a regular summing amplifier like this. Since now I can bring this negative here and make this positive, then that will be the circuit. And the output of the summing amplifier, Y of S. This is cascade realization of the same system. This is parallel realization. Which one is better? In terms of component, they probably have the same, 2 integrator, 2 summing, and this is 3, so not much difference. But here is the advantage of the parallel realization. See, this subsystem here will stay idle until this subsystem finish process the input. Then it give to here, then this will operate. But in this parallel realization, that's not the case. The input X of S here and here, I can connect them by one node. So I can just make a node here, and then this will be X of S. See, now in parallel realization, the input is seeing this system and this system at the same time. So both systems are processing the input at the same time. They don't have to wait. Then the outcome will be added here. So parallel realization usually faster than the cascade realization. So that's one advantage. The second advantage is the following. If some error happened in this subsystem, it will propagate to this subsystem. So this subsystem will also process the error that happened here. And usually when they are cascade, that error will be even amplified by subsequent subsystem. In this case, no. If there was error in this subsystem, these will not be affected by the error that happened here. So the total error here will be less. And it's a practice whenever you are designing and building a system, use parallel realization when it is possible. Okay, the last thing is, how do we move from these blocks diagram to an actual circuit that we build in the lab? If you take circuit theory or analog electronic, you use op-amp to build amplifier, subbing amplifier, integrator from an op-amp. So now that's the next topic. How do I move from this block diagram to an actual circuit that I build in the lab that will do what I desire? It take an input, process it, and it give me an output. We will be using the following circuit component for system realization using operation amplifier. From circuit theory, you have this op-amp with RF and R connected in the feedback terminal, and we learned the gain will be RF divided by R and its negative amplification. So that will be minus RF over R. If I connect the op-amp with a capacitor here and resistor here, then the output will be related to the input by this equation. So the output will be Y of S, K over S, X of S. That's an integrator. And K is a constant. I can choose the resistor and capacitor value to make it just -1. The third one is the summing amplifier. So this is this one. And a summing amplifier, the output Y of S will be minus RF divided by R1 times the input X1 of S minus RF divided by R2 times the input X2 of S minus RF divided by R XR of S. And that is a summing amplifier. So this is the circuit component we will be using for system realization. So if you have H of S and you use form 2 realization, this is the circuit you will be getting, just like the examples we did. Now I don't need to build a summing amplifier that has only 2 inputs. I can have a summing amplifier of 3 inputs or 10 or 15 inputs. So then I can redraw this circuit such that I don't need this one. I can connect this directly here and this directly here. So now I have a summing amplifier with 3 inputs, 1, 2, 3, and that will be this one. So if I want to draw this one, see, this summing amplifier will add these two components and the output will be added to X of S. So all I need, I can have one summing amplifier and it has these 3 inputs. The input X of S, this coming here the -4, and this here the -10. And then the output of this summing amplifier will go to an integrator, and the output of the integrator is the -4. So the output of the integrator is this -4. So let me write this here, change the order. So this is the -4, so it will be connected here. This is the -10, this is the X of S. So one output goes here, we did it, and one branch go to a 2 amplification, so another branch will go to an amplifier of 2, and another branch go to an integrator. So we cover this node. We are done with this. It has 3 branches, 1, 2, 3. Okay, now let's look at this branching. This is my second integrator, that's the output here. One go to the -10 amplification, so that will be this. Another branching go to an amplifier of 5, so I can have amplifier of 5. And the output of the amplifier of 2 and the amplifier of 5 is added by this summing amplifier. So then I have these two added by this summing amplifier, and that's the output, Y of S. Now the question is, this integrator is inverting. If you look here, it's negative, but in my block diagram, it should be positive. So what I can do is put an inverter here to offset this negative. So then I will delay these and these to be here and here. So I'm gonna have an inverter here. Same thing, the summing amplifier here, it's positive summing, but in my actual amplifier I'm building, it has a negative summation, negative. So I have to offset that negative sign here. So again, I can put an inverter here, -1. See, this negative inverter and negative inverter, they are connected in cascade so they can cancel each other. So I don't need them. So I don't need to have a redundancy, build a negative and negative, since they will be canceling each other. So I can really actually take them out. Now this summing amplifier, to have this -4, I can have an amplifier of -4 amplification. And that will be summing of 1. Same thing, this branch is -10, so I can put inverting op-amp here, so this will be this. And this summing amplifier will give me a negative value. So I have the option of building an inverter here to cancel this negative, or instead of having an inverter, I can make this inverting op-amp. So this will be -2 and this -5. This way, this negative here and negative here will cancel this inverter, so I don't need it anymore. And there are always different ways you can build it. Now, after you do this one, we can start with this summing amplifier and the gain all 1. So I can have this 1K, this is 1K, and this is the input, and this is all gain 1. So I can have also this is 1K, and this is 1K. So this branch is here, and this branch is here. And that is the summing amplifier. Go to an integrator, which is a resistor and a capacitor. And again here the gain is 1, so I can choose this 1 microfarad, and this is 1 mega ohm. And from this node, this amplifier, and I can have a resistor here. The gain is 4, I can have this 16K and this is 4K. That will give me gain of -4, and it's connected to this terminal, so it is connected to one of these terminals. This is integrator, of course. Then I go from this integrator to this inverter. And gain of 2, I can make this 10K. This is 5K, gain of -2. So this is here. Now let's build this one. This is integrator of gain 1, actually -1. So I can make this 1 mega ohm. This is 1 microfarad. So that is here. And then this branch will be a gain of -10. So I can make this 10K and this is 1K and connect it here. Okay, now this branch, inverting op-amp of gain 5. So I can make this 5K and this is 1K. Then they go to the summing amplifier. And the summing amplifier gain is 1. So 1K, 1K, 1K. And that's the circuit. Here we make this connection here. Minus, plus, ground. And this is the circuit that represents this block diagram and that represents this system using form to realization. Well, this is the end of system realization. First block realization, use canonical form 1 and 2 and the transpose, and then moving from a block realization to an actual circuit diagram. Thank you for watching and see you in next video, which will be filter design by poles and zero. In this one, the client will come to you and he said, I have this input, I want this type of output. Can you build me the system? That means you have to come up with H/S. And that is system design. And there are different ways of designing, but here in this course, we will use the poles and zero positioning method. See you next video, and that will be the last video for Laplace transform. Thank you.